Good evening, Lamai. Today we are going to discuss about liquefaction of gases. Right, this is going to be the last lesson with the gaseous state of matter, unit 5, right? Unit 4, sorry. Right, let's first discuss about what this liquefaction means. Right, the liquefaction means actually converting your gas into a liquid. Right, liquefaction means, right? Liquefaction means converting a gas into a liquid. Right, this is what liquefaction means. Right, so when converting a gas into a liquid, actually what happens is think of the particle arrangement, right, of a gas and a liquid. Right, in considering a gas, right, you would see this kind of particle arrangement where the particles are bit away from each other. This is the situation with the gas, right? And these guys are moving here and there, right, like this. Random motions can be seen with the particles of a gas. This is how a gas looks like. So liquefaction means converting this thing, right, to a liquid. So if you convert this into a liquid, these gas molecules will be arranged much closer to each other, like this. The same number of gas molecules will arrange much closer to each other. Right, this is the nature of a liquid. Right, you would see some strengthening of the intermolecular interactions when it comes to a liquid, right, compared to the gaseous state. So when converting a liquid, you are supposed to increase the intermolecular interaction strength like this, and you are supposed to put the particles much closer to each other, right? So when you are doing the liquefaction, that is what happens. In a gas, the intermolecular interactions are very weaker, but in a liquid, you would observe some greater attractive forces among gas molecules, and the gas particles, those are close to each other compared to a gas. So this is what happens when you are to liquefy the gas. So liquefaction of gas means this: converting your particles which are a bit far away from each other and moving with very high speeds, right, to a liquid where the particles are very close to each other and moving in very slow speeds. So this is what happens when you are doing a liquefaction, right? So normally you can do this kind of a liquefaction, do this kind of a change by decreasing the temperature as well as increasing the pressure, right? Why is that? Because here your particle movements are high, that means kinetic energy is high. Here the kinetic energy is low. We know the kinetic energy is actually a measure of temperature. That means your temperature is high with a gaseous system, but when it comes to a liquid, the temperature is low. This means actually you can liquefy a gas by decreasing the temperature. By decreasing temperature, you can liquefy a gas, right? Temperature should be decreased to liquefy a gas. And what about the pressure? What about the pressure change you can do to come up with a liquid starting from a gas? So basically, when it comes to a gas, your concentration is low. In unit volume, you have very less number of particles. Concentration is low. Concentration is a measure of pressure, right? P is equal to CRT. So in a gas, your pressure is actually low, right? You know the reason is P is equal to CRT. is a constant temperature. P is proportional to concentration, right? When it comes to a liquid, in unit volume you have more particles. The same particles are appearing in a lesser volume. So in unit volume you have more number of particles. So concentration is high when it comes to a liquid. So that means your pressure is high compared to the gaseous state, right? As P is equal to CRT, right? Okay. So you can liquidize a gas by increasing the pressure. So that is the pressure change you can do for a liquefaction, right? So this is the normal scenario, right? So one may think, right, that any gas can be liquidized by decreasing temperature as well as increasing the pressure, right? So that idea is true for some extent. Most of the times, this idea is true. By decreasing temperature as well as increasing pressure, yes, you can observe a liquid formation. But Lamai, there are instances, very special instances, even though you are applying kind of infinite pressure, still you are unable to liquidize your gas, right? There are some special instances where even though you are applying enormous pressure, that means you are trying to put the particles very close to each other. Greater pressure means particles become closer to each other, right? So even though you have to apply enormous pressure, infinite pressure, still some temperatures are there where you cannot liquidize your gas, right? So that is a special situation we are going to discuss about this thing, right? So what is that special situation, right? The point is this, Lamai. So even though you are trying to put the particles very close to each other by increasing the pressure, right? By only closing the particles together would not give you a gas. Only by putting the particles very close to each other, you are not going to observe a liquid formation. Why is that? Because to consider the physical state as a liquid, there should be interactions between the particles as well. Without these intermolecular interactions, this is not going to consider as a liquid. This is not a liquid, right? To consider it as a liquid, you should observe these intermolecular interactions as well. So if your temperature is very high, then you are unable to have those interactions between your molecules. If your temperatures are very high, the particles are moving at very high speeds, so that you are unable to have those attraction forces among those particles. Why is that? Less interaction time, right? When the speeds are very high, minimum interaction time available. The interaction time is not there when the speeds are very high. So you can't have intermolecular attractions as well as repulsions, right? So if your temperature is a very high value, then even though you are applying enormous pressure, even though you are applying infinite pressure, and you are trying to put the particles close to each other, still you can't observe the liquid formation because you can't have those attractive forces among particles. So it can't consider as a liquid, right? When the temperature is that much high, right? So, right, normally we can liquidize a gas by increasing the pressure, but remember that that can be done only if your temperature is with some value which is not beyond, right, a value which can't have the interactions among particles, right? Okay, the idea is clear, right? So let's go to the right note there. What they are saying? They are saying, right, the note says, we may think that liquefaction of a gas can be done just by cooling and compression, just by decreasing temperature and increasing the pressure, right? So that is how a normal guy would expect to liquidize a gas, right? Although it is correct to some extent, it is said, right, liquefaction by a compression is possible only if the temperature of the gas is lower than its critical temperature. Temperature of a gas is lower than its critical temperature. Let's discuss about what this critical temperature means. What this critical temperature means? Actually, the idea is this. The critical temperature is actually the maximum temperature, right? The maximum temperature you can have with the attractive forces among particles. The maximum temperature of a system there can be with the attractive forces among particles, among molecules. If the temperature is beyond that maximum value, if the temperature is beyond that critical temperature, the maximum value allowed, then the molecule speeds are so high you don't have available interaction time to have those molecular attractive forces, so that you can't liquidize your gas by even applying infinite pressure there, because you can't have attractive forces as the temperature is very high, right? So again, I'm telling you, the critical temperature is the maximum temperature at which a gas can be liquidized. Or one can say the maximum temperature at which the intermolecular forces, attractive forces, exist among gas molecules, right? Again, I'm telling you, what is the critical temperature, right? The critical temperature means, right? Critical temperature means, right? Critical temperature normally we denote it with TC, critical temperature. It means that is the maximum temperature at which maximum temperature at which a gas can be liquidized by applying pressure. By compression, right? This is the textbook idea, right? So one can say, so to have a greater picture of the critical temperature, right, one can say, right, this is the maximum temperature at which right the molecular interactions, the molecular attractive forces exist to liquidize a gas, right? Beyond this temperature, right, you don't have the interaction time to have those attractive forces. Beyond this critical temperature, the molecule speeds are so high so that you don't have enough interaction time to have those molecular attractive forces among the gas molecules, so that you can't liquidize your gas, right? So this is the idea of the critical temperature, right? It's a maximum temperature. It's a maximum temperature. Highlight this thing. It's a maximum temperature at which a gas can be liquidized by applying pressure. So that is the maximum temperature at which the molecular attractive forces exist to liquidize a gas, which is enough to liquidize a gas, right? Okay, so just write this stuff down. Maximum temperature at which a gas can be liquidized by applying pressure. That is critical temperature. One can say this is the maximum temperature at which the molecular attractive force exists to liquidize a gas. Right, exist, you can write like this, exist. Which is enough to liquidize a gas. Which is enough to liquidize a gas. That's better. That will give you the better picture, right? Okay, the idea is clear, right? The next point. So actually this critical temperature is with a relationship with the secondary interactions, the strength of secondary interactions. So let's discuss about that thing as well. Critical temperature and strength of secondary interactions. Right. So what is the idea here? Lamai, just think of this example. Just think of this example where you have a gaseous system with O2 gas and a system with, right, let's say CH4 gas. Just think of which system is with a greater critical temperature. Just think of which system is with a greater critical temperature, whether the O2 gas system or the CH4 gas system, the greater critical temperature. The idea is this. So among not the O2 gas, let's consider H2O gas is better, right? H2O gas and the CH4 gas, right? Among H2O gas molecules, if you think of among H2O gas molecules, there will be much stronger attractive forces. The hydrogen bonds will be available. Hydrogen bonds will be available, right? So among CH4 gas molecules, much weaker interactions, London forces will be available. So which gas comes up with a greater critical temperature? Which kind of interactions can stand even for higher temperatures, even with the higher temperatures? This one or this one? The idea is this. When the temperature is high, particles start to move with high speeds, less interactions time. But if your intermolecular force strength, the secondary interaction strength is high, then even with very minimum amount of interactions time, still you can have your interactions, the attractive forces among your particles, right? If your particles will bound strongly together, these bonds can stand even in high temperatures. Even in high temperatures, these bonds won't break. They can stand when the interactive strengths are high, right? Interaction strength is high here, so can stand even at higher temperatures, right? Without breaking your bond, they can stand even at higher temperatures. So that the maximum temperature you could have with your second interactions available is kind of a higher value for this system. So your critical temperature will be a higher value for this system. You can stand even at higher temperatures with the attractive forces among your particles, as your attractive forces are very strong. So the maximum temperature at which you can have those molecular attractive forces with your system is a greater value. So your critical temperature is a greater value when you are with a greater interaction strength among your gas molecules. The idea is clear. The opposite happens with this one. The opposite happens with this one, right? With this system, your interaction strength is low. Right? So can't stand at higher temperatures. Those will break. So the maximum temperature at which you can have those interactions is kind of a lower value. So the critical temperature, that is the maximum temperature at which you can have those second interactions among your particles, that's a lower value. Right now? So when the second interaction strength is high, your critical temperature is high. That is the idea. When the second interaction strength is low, your critical temperature is low. Right? So have that idea. So let's note that thing. So you can write, right? The relationship between the critical temperature and the second interaction is like this. When secondary interaction strength when that thing is high, your TC value, critical temperature, is high, right? That is the final idea. Right? If you need an example, you can copy this thing. Example, critical temperature of H2O is a greater value than the critical temperature of CO2. Sorry, CH4. In this case, I had taken CH4. Right? Here, just the hydrogen bonds are there. Here, the London forces are there. The idea is clear, right? Okay. So just complete this note, Lama. Right. Okay. Let's discuss about the next subtopic, the critical pressure. Right. We had done with the critical temperature. We had got the idea about the critical temperature. Now let's move towards the critical pressure. Right. Critical pressure. Right. What this means. Right. Critical pressure. Another critical value. Right. Right. Critical pressure. Which is denoted by PC, pressure critical. Critical pressure. What this means. Right. It is like this, Lamai. Actually, critical pressure is the minimum pressure. It's the minimum pressure you need to apply to liquidize your gas at the critical temperature. So first write the definition. Just write with me. After that I'll explain. Right? Critical pressure is the minimum pressure right that should be applied to liquidize a gas at critical temperature. TC. That is the definition. So critical pressure is the minimum pressure you need to apply to liquidize your gas at critical temperature. Right? Let's see. You have a gas at critical temperature. Right? You have gas at critical temperature. The picturized idea is this. You had a gas at critical temperature. Right? Let's see. Gas at TC. So you are applying pressure. You are applying pressure. You just let's say you just apply the pressure. Let's say this is a piston system. Right? You are just applying pressure. You are applying pressure. So at some instance, your gas will liquidize. Let's see. When applying this amount of pressure at some instance, right? Some liquid is formed. Right? So this pressure, the pressure at this instance, the first instance you observe the liquid at critical temperature is referred to as the critical pressure. That pressure is referred to as the PC. Right? You had a gas at critical temperature. You had applied some pressure to liquidize your gas. Right? The pressure at which you first see the appearance of the liquid is referred to as the critical pressure. So that is going to be the minimum pressure you need to apply to liquidize your gas at critical temperature. Right? Okay. If you apply more the pressure, definitely there should be a liquid. The first instance of appearing the liquid, this which will be appeared at the minimum pressure you applied. right? So critical pressure is kind of a minimum value, the minimum pressure you need to apply to liquidize your gas at critical temperature, right? Okay, it's a minimum pressure that should be applied to liquidize the gas at critical temperature. The idea is clear, right? Okay, right, that is all about the critical pressure, right? So let's come up with some example there. Let's come up with some example to have this idea clearly, right? Let's come up with this example. Right, just consider a gas, with its critical temperature is equal to 500 Celsius and critical pressure is equal to 10 atm. Just think of this kind of a gas, right? Let's consider some three conditions, whether you are able to see the liquid appearance or not. The liquefaction. Let's discuss about these things. Three situations. When Tc is equal to 600 Kelvin and Pc is equal to, let's say, 1580. Second instance, when Tc is equal to 500 Kelvin, right? This Kelvin or Celsius, anything, right? Let's say Celsius, right? As we came up with the Celsius, right? And Pc is equal to 580. And another instance, when Pc is equal to 500 Celsius and Pc is equal to 1580. Let's discuss whether you are able to see the liquefaction process, whether you are able to see the liquid appearance, right? What about the first condition? Can you see the appearance of the liquid at 600 Celsius and when you are applying 15 atm pressure? The critical values are given like this, right, for the gas. Even though you are applying a greater pressure, right, than the Pc, right, but you won't be able to see the liquid formation. You won't be able to see the liquid formation. Why is that? The reason is your critical temperature. Your critical temperature is actually greater than, sorry, your temperature is greater than the critical value. So this is not the critical, right? Sorry for that, right? Just temperature values, right? Right. These are some conditions. These are the critical values, right? So your if the temperature is greater than, if your temperature is greater than the critical value, then even though you are to apply, right, infinite pressure, still you are unable to liquidize your gas. Even though you put the particles very close to each other, still the liquefaction of gas won't occur, as you are unable to form the molecular attractive forces. As your particles are moving with very high speeds, no interaction time available to form the bonds. That is what happens with this situation. Your temperature is greater than the critical value, right? So you won't see the production of liquid at this condition. What about this thing? When the temperature is same as the critical value, the temperature is same as the critical value, That means, yes, you can form bonds. Yes, you can form bonds. That means you can liquidize if you are to apply the minimum pressure needed. If you are to apply the minimum pressure needed or more than that, you can liquidize your gas, right? Because your gas is at the critical temperature. Gas is at the critical temperature means only if you are to apply the minimum pressure needed or more than that, yes, you can liquidize, because you can still form intermolecular interactions as your temperature is not beyond the critical value, right? So temperature is okay, but the problem here is this thing. Even though this factor is okay now, we have problem with this one. Why? You are not applying the minimum pressure needed to liquidize your gas at critical temperature. The minimum pressure needed to liquidize your gas at critical temperature is 10 atm, but now you are applying just only 5 atm, right? So that you can't liquidize your gas. Even though it is at the critical temperature, you can't liquidize your gas because you are not applying enough pressure. You are not trying to put the particles close to each other. That is not enough, right? By such a low pressure, right? So because of the pressure factor, you're not applying the pressure needed or beyond that, right, to liquidize the gas. So that with the pressure factor, this condition fails to liquidize your gas. What about the third situation? Yes, your temperature is at the critical temperature. Yes, you can form the secondary reactions to liquidize your gas, and the pressure is actually a greater value than the minimum pressure needed to liquidize the gas. So pressure factor is also provided. So in this condition, yes, the gas can be liquidized. You would observe the gas there. Sorry, you would observe the liquid there. Right now, the idea is clear. As temperature is at the critical temperature, that means you can have those second interactions. Second reactions will exist with this temperature, right? So as you are providing more than the minimum pressure needed to liquidize the gas, yes, you can, right, liquidize your gas, right? Okay, so let's complete this stuff as well. Right, that is all about what you should know about the critical pressure, right? Let's concern about the next critical value, that is the critical volume. Next thing, the critical volume. right? The third critical parameter is the critical volume. Right, VC, volume critical. And that is the volume. It is the volume of the fluid which is formed at the critical temperature and critical pressure. Right? It's a very specific volume. Right? That is the volume of the fluid which is formed at the critical temperature and critical pressure. If you are applying the critical temperature, at the critical temperature, if you are applying the critical pressure, some fluid will be formed, right? The volume of that stuff is referred to as the critical volume. Normally it is a molar volume, more the number of moles, right? The volume will be greater, no? Right? So it is kind of a extensive property, no? Right? So amount of matter matters, right? So critical volume is a constant value, right, for a given substance, right? So critical volume is the volume of fluid which is at critical temperature and critical pressure, right? So that is the critical volume, right? So basically it's a molar volume, right? Volume of 1 mole of substance, right? Okay, just complete this stuff. Volume of the fluid which is formed at the critical temperature and critical pressure. Right now, the idea is clear. That is the critical volume. Right. So we have just completed the discussion of critical parameters. Right. Now let's discuss about the phase diagrams. Phase diagrams of substances. Actually, the phase diagram stuff is actually to discuss at the unit 12 with the equilibrium lessons, right? But some little introduction is given at the unit 4 of your resource book, right? So we have to discuss that little introduction they have given for the phase diagrams, right? So let's discuss about that thing as well. The next topic is the phase diagram. So let's consider phase diagram of water. Right. So let's this is our major topic today, right? Phase diagrams, right? Clear, yeah? Phase diagrams. Right. Okay. Right. Let's consider about the phase diagram of water. Right. The phase diagram of water. Phase diagram of H2. Right. So phase diagram is this kind of stuff, right? Where all the phases of your chemical substance will be represented in a one single diagram, right? So normally at this axis you have the temperature, in the phase diagram, right? At this axis you have the pressure. when varying the pressure and the temperature, you could see the transformations among phases, no? Liquid to solid, solid to gas, right? Like those things, liquid, solid to liquid, liquid to gas, gas to liquid, liquid to solid, can be done when you actually change the pressure and the temperature, right? So those things will be discussed with these phase diagrams, right? So this is the phase diagram of, right, water. Let's say the phase diagram of H2O, right? This kind of phase diagram would appear with H2O, right? Let's discuss about the regions and the special stuff with these phase diagrams, right? So a little bit here. When concerning phase diagrams, right, I'll mark these things, right here. When concerning these phase diagrams, right, first of all, we should be able to label these three regions, right? This region and this region and this region. Three regions are there, right? Region 1, 2, 3, right? So we should be able to correctly label the three regions appearing in your diagram, right? So those regions are belongs to, one belongs to the solid state, the other belongs to the, one belongs to the gas state, and the other belongs to the liquid state, right? Now we are supposed to label this stuff. So let's discuss how to label this one. We are not going to memorize this stuff. We should come up with a better way to label this diagram, right? It is like this level. So first let's try to label, right, this section and this one, right? Just take a point like this, just take a point like this and a point like this. This point appears at this section, right? This point appears at this section. So let's consider whether this represent a solid, liquid or a gas. Now this is a very high temperature. This point appears at a very high temperature. Towards this side the temperature increases now, right? Towards this side the temperature increases now. So this point appears at a very high temperature and a very low pressure, This appears at a very low pressure, right? Very high temperature, very low pressure. So which kind of a phase will exist with a very high temperature and very low pressure? Very high temperature, that means kinetic energies of particles are very high. The particles are moving with very high speeds. And very low pressure means concentrations are very low. The particles are very far away from each other. What is that physical state? The particles are moving with high speeds. Particles are very far away from each other, very low pressure, low concentration. That is the gaseous state. So this region represents the gaseous state. So this is about the gaseous state. So that is how we are supposed to label this section, right? So this point belongs to this section, this point belongs to this section, this point belongs to this section. So if this point representing a gas, this whole section should represent a gas. This is the idea. Yes, this point represents a gas, because very high temperatures, that means very high kinetic energies among particles, and very low pressures, that means very low concentrations, means your particles are far away from each other. The molecular distances are greater. Low concentration means that, no? Right? So it's the gaseous phase, gaseous state. What about this point? So this point represents a very high pressure and very low temperature, very high pressure. Very low temperature means the kinetic energies of particles are very low. Low temperature means kinetic energies of particles are very low. Minimum movements among particles. Then when high pressure means, very high pressure means the concentration is high. That means particles are very closely packed, very close to each other. Concentration high means like that. Concentration high means the particles are very close to each other, right? So you could see some highly concentrated. This is the concentration is very high. In a unit volume, you have more particles, right? This is a situation with low concentration. In unit volume, less particles, right? No? So concentration is very high. Pressure high means concentration is very high. That means more particles in unit volume, so that particles are very close to each other. So particles are very close to each other, and particle movements are very minimal. Less movements among particles. That means it is the solid state. It is the solid state, right? So this point represents a solid state. That means this whole section should represent the solid state. That whole section should represent the solid state. Right now? Ideas clear? Then the rest, the in-between state should be the liquid state. So that is how we are supposed to label the three sections of your phase diagram. The three phases available with the chemical. Right now? That is done. Avulak naha edit karaganna puluwan. Right. Okay. That is one. Right. One thing you should learn about the phase diagrams, right? Phase diagrams කියන්නේ ඔයාලා දැනගන්න පළවෙනි කාරණේ කතා කරේ, right? You should be able to correctly label the sections available in your diagram. That is done. Right. Then let's discuss about these three lines or curves, as well as some special points, these things appearing in your phase diagram. Let's discuss about this. Right. So this point is referred to as the critical point. This is referred to as the critical point. Right. Is referred to as the critical point. And this point C is referred to as the critical point. Critical point. Right? And the temperature of the critical point is referred to as the critical temperature. And the pressure related to that critical point is referred to as the critical pressure. Now you see that now? The critical point, right? So this is the maximum temperature at which a gas can be liquidized. Beyond that, liquid state won't appear. Beyond this point, beyond this temperature, liquid state won't appear. If a temperature is less than this, like this, yes, liquid state appears. See, liquid state is there. With this kind of a temperature, yes, liquid state is appearing. But beyond this temperature, like this kind of temperature, beyond the critical temperature, you won't see the liquid appearing. So you can't liquidize your gas if your temperature is greater than the critical temperature. Idea is clear? So that is the critical temperature, right? The maximum temperature at which a gas can be liquidized. Gas can be converted to a liquid by applying pressure. See, if you are with this kind of a temperature, say, and with this kind of a pressure, if you are at this kind of a temperature and this kind of a pressure, let's see, so your system appears at this point, right? So that temperature is a temperature lesser than the critical temperature. So by applying pressure, by increasing the pressure, by applying pressure means there's an increase in pressure, you can move this one to a liquid, this point to a liquid. See, if you increase the pressure from here to here, right, at this temperature, which is a lesser temperature than the critical temperature, yes, you can liquidize the gas. This point will move from here to here. If you increase the pressure by keeping the same temperature, if you increase the pressure, this point will move from here to here and get liquidized. Right now, right? So you can liquidize a gas if your temperature is less than the critical temperature by applying pressure. Right now, okay, the ideas are clear. So, and this point is the critical point then. So this is the critical temperature. Beyond that temperature, the liquid state won't exist, so you can't liquidize the gas. Right? The idea is clear, right? Okay, what else we can think of with this diagram? Right? Okay. Critical point and critical pressure, those are there, right? The critical point and the critical pressure and critical temperature, those are things, right? Now what is now? Next one, right? Next thing, let's discuss about these three lines. This is about those three lines, right? OA line, OB line, and the OC line. This is about those three lines. What are those lines representing? Right? Yes. The OA line is actually representing you the state, the physical state, which is with the solid and the gas, the equilibrium state which is with the solid and the gas. So it's like this. So any point on this line, it belongs to the solid state as well as to the gas state. If the point is on this section, yes, that is representing only a solid. If a point on this section, that is representing only a gas. But any point on this line will represent both a solid and a gas. Both a solid and a gas. So it's a situation where solid and gas both are there in the system. Normally those are referred to as equilibrium systems. What about OB? It's like this. So when it comes to OB, right, line and the stuff, right? If you are with this, if this point appears at this, that is a solid. If a point belongs to this section, it's a liquid. If your point appears on this line, that means if you are regarding this temperature and this pressure, right, that means your point appearing on this line, on the OB line, then that system, and in that system both the solid and liquid will appear. Both solid and liquid will appear. So it is a situation where both the liquid and solid is at equilibrium, right? So this line representing a liquid gas equilibrium, right? So this line is representing liquid gas equilibrium, this line representing solid liquid equilibrium, and this line representing solid gas equilibrium, right? Those are the things done by those three lines. And if you want to name these lines, one can say, or one can name, or one can label this line as the melting point line or melting point curve, right? Melting point curve. One can say the OB line as melting point curve. Actually, that OB line will give you the melting point, right, at the considering pressure. So let's say you are, right, concerned in this pressure, let's say you are considering this pressure, right? Some kind of pressure, right? 3 atm or something. At that pressure, your solid starts to convert to liquid at this temperature. If your temperature is less than this temperature, you are dealing with a solid at this 3 atm situation. If your temperature is beyond this exact temperature, you are dealing with a liquid. Actually, that this temperature is where the transformation occurs, solid converting to liquid. So that is referred to as the melting point. It is referred to as the melting point. So this is the melting point at 380 a specific pressure, right? So this line will give you the melting points of corresponding pressures. So one can say it is as the melting point curve. So if you are thinking of this kind of a pressure, right, 280 or something, then this is the melting point at 280. This is the melting point, melting temperature at the 280. So the solid converting to liquid at this temperature. Beyond that temperature, it's a liquid. Before that temperature, at 280 m, it's a solid. So solid converting to liquid happens at this specific temperature. It is the melting point of this substance at the 280, right? So one can say it is as the melting point curve. Like that, this curve representing the situation where liquid turns to a gas. So let's consider about the 380 m situation. So this point, let's consider about this temperature here. So this temperature is a very specific temperature. Why is that? If your temperature is less than this at 380 m, you are dealing with a liquid. If your temperature is less than this, see, this kind of temperature, at 380 m, you are dealing with a liquid. If your temperature is greater than this value, at 380 m, you are dealing with a gas. So transformation of liquid to a gas occurs at this specific temperature. So transforming a liquid to a gas means it is the boiling. So this is your boiling point at 380 m. At 380 m, right? So if you are thinking of 280 situation, this is the boiling point at 280 m. This is the boiling point at 280 m. At this temperature, the transformation of from liquid to gas occurs at 280 m. Before this temperature, right, at 280 m, it's a liquid. After this temperature, at 280 m, it's a gas. So this is the specific temperature where the liquid turns to a gas at 280 m pressure. So this is the melting point at, boiling point at 280 m, right? So this OC curve giving you the boiling points. So one can say it is the boiling point curve. Boiling point curve. You have the melting point curve and then the boiling point curve, right? And this is actually the sublimation curve, sublimation or deposition curve. So converting a solid directly to gas, it's a sublimation. Converting solid to directly to gas. So any point on this line representing a sublimation temperature, right? So OA is the sublimation or deposition. Deposition means converting the gas directly to solid, right? Temperature curve. Those are three special curves. At the melting point curve, there will be equilibrium between solid and the liquid. At the boiling point curve, any point on that curve, the OC curve representing the equilibrium of liquid and gas, right? Any point on the OA curve representing equilibrium between solid and gas, right? No? Okay. So what about this O? What about this O? This special point. So at that point actually belongs to all the solid, liquid, and gas. This point belongs to all the 3 points, 3 phases. So there you would observe the solid, liquid, and gas. All the things are appearing at the same system. So it is referred to as the triple point. It is referred to as the triple point. So O is referred to as the triple point, where all the 3 phases exist. All 3 phases. Solid, liquid, gas at equilibrium. All the 3 phases are at equilibrium. Right, at the triple point. Right? All 3 phases are at equilibrium. All 3 phases exist. So for water, it's a specific value. For any substance, the triple points is a specific value. Right? So we'll write that thing as well in our diagram clearly. Right, I am erasing this stuff, right? So when you are writing, just write do the diagram correctly, right? Clearly. Right. Is our diagram now? Or is there so solid? Right now. So this is the triple point, right? So triple point temperature is important to know. That is 273.16 Celsius. Sorry, Kelvin. Sorry for that. Kelvin, right? Okay. So let's discuss about the 180 situation, right? So normally your 180M is appearing at this kind of a situation. With water, right? This is 180M, right? So that these values are very specific values with 180M, right? So I'll write this one with a different color, right? Triple point. So this is the temperature where you convert the solid to liquid at 180M. So that value is what? 0 Celsius. That value is 0 Celsius. Your melting point. What about this? At this temperature, at 180M, the transformation of liquid to gas occurs. So this is 100 Celsius, what we know, the boiling point, right? And this is your triple point, special value, and this one is the pressure at the triple point, right? This 0.06 atm, right? 0.06 atm. Right now. So this is your phase diagram. Just complete the stuff. So this is triple point, right? You have the gas here. Right. So first of all, just draw this one. Mega clearly මේ පින්තූර ඇද ගන්න මුලින්ම. ඊට පස්සේ අපි මේ ගැන කතා කරමු තව ටිකක්. Right. It's gas, right? Let's draw this diagram. Right, no? So let's discuss a bit more about this triple point and the stuff. Triple point is how you can put D they all take right? So we had said that this line represents the deposition temperatures or the sublimation temperatures, right? This OA line actually represents the temperature where the deposition occurs or the sublimation occurs, where the gas directly converting to a solid, it's a deposition, or where the gas directly, solid directly converted to gas, it's a sublimation without coming up with the liquid, right? So any point on this line gives you the deposition or the sublimation temperature, right? That is clear now, right? So let's discuss some relationship, right, of these pressures, some relationship of pressure where we are able to see the deposition and the sublimation, right? So it's like this, Lama. So when your pressure, when your considering pressure, right, is less than, when your considering pressure is less than the pressure at the triple point, less than the pressure at triple point, right? When your pressure is less than the pressure at triple point, right, what will happen? So it's like this now. So pressure at triple point is 0.06 atm. If your pressure is less than that, say, consider this kind of pressure, this kind of pressure, the pressure is less than the pressure at triple point, right? Then if you are with a solid, when increasing temperature, let's say you are with a solid with this temperature, when increasing temperature, you clearly see that you won't obtain a liquid before coming up with the gas. So when your pressure is less than the pressure at triple point, when you are increasing temperature, that means this point goes towards the right, then you directly come to a gas, right, not going through a liquid, because Lamai, in pressures less than the pressure at the triple point, the liquid phase won't exist. With any pressure which is less than the triple point, liquid phase won't exist, right? So this is the pressure at, right, the triple point. Any pressure less than the pressure at triple point, you see, liquid phase won't exist. Only the solid and the gas appears, right? So when considering any pressure which is less than the pressure at the triple point, you observe only the solid and the gas appearing. So the solid will directly convert to a gas when the temperature is increased, and gas will directly convert to a solid without reaching liquid when the temperature is decreased. Right? So sublimation deposition happens only at temperatures which are less than the temperature, only at pressures which are less than the pressure at the triple point. Right? No? The idea is clear? Right. So we can write that thing. When pressure is less than pressure at the triple point, few things happen. What are the few things? Liquid state won't exist. Right? If temperature of a solid is increased, sublimation would occur. Sublimation that means converting the solid directly to a gas occurs if temperature of a gas is decreased, right? Deposition which means converting the gas directly to solid occurs. So sublimation and the deposition occurs only when your temperature is less than the pressure at the triple point, as liquid state won't exist there. Right now? So you can complete this stuff as well. Right? That is how sublimation and the deposition occurs. At temperatures greater than the at pressures greater than the pressure of the triple point, right? You would observe all the three states of water, right? No? So that is those are the ideas we need to know about the phase diagram of water, right? Phase diagram of water, right? No? So that is all you should know about the phase diagram of water, right? So with this, right, we are ending this section, right? The phase diagrams, the liquefaction and the phase diagrams, right? Now, okay, let's complete the outline. Right. So next session is end. Right. Then we'll discuss about the gas laws, the Boyle, Charles, and Avogadro, the gas laws. Right. Let's discuss about the gas laws. Right. And the graphical forms related to those gas laws. That is our next discussion, right? Actually, that session is there in your note at the page number, right? At the page number 6, 7, right? You could see this note, right? It is all about gas laws. Some ancient laws. Under this, we are going to study two things. The first thing is about the major three gas laws, Boyle, Charles, and Avogadro's law. Right? Then we can combine those things to come up with the combined gas equation as well. As well as because in NRT we can derive from the three gas laws, right? We'll discuss about those things, gas laws. And then ultimately we'll discuss about, right, the graphical forms. Graphical forms with these pressure, temperature, volume, and moles relationships, right? Okay. Let's first discuss about the three gas laws, right? The three gas laws. First, the Boyle's law. Right? Three gas laws are Boyle's law, Charles' law, and the Avogadro law, right? So let's discuss one by one. Boyle's law. Boyle's law. Right? It is kind of a PV relationship. Boyle's law is kind of a PV relationship. Right? So Boyle's law we can write. It is the right pressure volume relationship. We can say, right, when considering a gas, let's say constant amount of gas, constant amount of, one can say constant mass. Amount means mass even, right? Moles or mass of gas at constant temperature right? So if the amount is constant, temperature is constant, right? We can apply this now. PV is equal to nRT, right? So if the amount is constant, that means N is constant, temperature is constant, so this is a constant. So we can write PV is equal to constant K, right? Or one can write P is equal to K over V, right? So we can get rid of this constant by applying a proportionality sign, right? So this is referred to as the right? Boyle's law. Right, this is the Boyle's law. PV relationship, right? When considering a constant amount of gas at constant temperature, we can say pressure is inversely proportional to volume. Pressure is inversely proportional to volume. Proportional to volume. That is the Boyle's law, right? That is the Boyle's law. So no need of memorizing this stuff, right? Boyle's law, Charles law, and the other law, right? Actually, these are relationships between two variables of the P equals nRT. So P equals nRT is kind of a 4-variable equation, no? Right? The pressure, volume, number of moles, and the temperature. With these gas laws, what we are doing is actually we are coming up with some 2-variable relationships. To come up with 2-variable relationships, the other 2 variables should get constant. To come up with only 2 variables, the other 2 variables, as P equals nRT is kind of a 4-variable equation, the other 2 variables, right, should get constant. That is what they have done here. To come up with a pressure volume relationship, you have to keep the other 2 variables in NT as constants, right? If the N and T are constants, PV is equal to K, or P is going to be inverse proportional to 1 over V, right? P is proportional to 1 over V, or inverse proportional to volume, right? That is the Boyle's law. Let's come up with the Charles law, right? Let's come up with the Charles law. So Charles law means it is the BT relationship, right? So to come up with the BT relationship, you have to keep the other 2 variables constant. The other 2 variables means pressure and the amount of matter, number of moles should get constant, right? So that is a Charles law, right? Let's write the stuff, right? When considering a constant amount, number of moles of gas at constant pressure, right? So when amount kept constant, number of moles N, and the pressure kept constant, we come up with the relationship between the other 2. So it's like PV is equal to nRT, right? This one and this one kept constant, amount of matter and the pressure. V is, so we can write like this now, V is equal to nRT over P. When these 2 are constant, this is a constant. So we can write V is equal to KT, or to get rid of the K, we can write V is proportional to T. That is Charles law, right? We can write volume is proportional to absolute temperature. What is proportional to absolute temperature, right? That is the Charles law, right? No? And let's come up with the Avogadro's law as well. So coming up with these 3 gas laws are very easy stuff, right? There's not much harder stuff, right? Don't consume much of time to study this one, right? So That's what you need to remember is, right, the two variables you relate with each and every gas law, right? I'll give you a hint for that thing as well. Avogadro's law. It's a V-N relationship, right? So this is it's like this line. So PV is equal to NRD, you know. Boyle's law is the PV relationship. Charles' law is the VT relationship. Avogadro's law is the VN relationship. First the corners. VP, VT, then the center, VN. Three laws are Boyle, Charles and Avogadro. Right? Keep these three things in order. Boyle, Charles and Avogadro. The first relationship is about VP. Second relationship is about VT, the two corners, then the center, VN. Right? So discuss about the relationship of two variables. The other two variables should get constant, so that you can come up with this one as well. You can write it like, when considering gases at the other two variables, constant pressure and constant temperature, right? Constant pressure and constant temperature. Then we can think of the other two variables, no? The Vn. So Vn is actually kind of a, so PV because in RT, no? So Vn in a kind of a relationship, right? Relationship. So we can write the volume is proportional to amount of gas. Right? Or one can say equal volumes of gas contain equal amount of gas particles. The same thing, right? Equal volume of gases contain equal amount of gas particles, right? Same stuff, right? So if you derive this stuff, we can write it as PV is equal to NRD, what we know, and as these things are kept constant, we can write V is equal to NR over, sorry, RTP over, like this, N. So as this is a constant and P and D are constant, so we can write V is equal to Kn, or V is proportional to N, right? So this is Avogadro's law, right? Derivation with the use of P equals NRT, right? Okay, so just complete the stuff, Laman. I think these things are appearing in your right note. Things are clear. Right. Okay. So these are easy stuff, right? Not that much hard. But actually, we can come up with the P equals NRT by combining these three gas laws, right? Let's discuss about that derivation as well. first the derivations, but our major focus today is not about these derivations, right? But to come up with the graphical forms, to clearly understand the graphical forms. That is our major discussion today. But anyway, first of all, let's do the simple stuff, right? Complete the simple stuff, right? Okay, let's try to derive the Picus NRT, the ideal gas law, with the use of these three gas laws, right? I'll try to derive the ideal gas law with the use of these three gas laws, right? That is very easy stuff, right? Okay, so deriving ideal gas law, right? Ideal gas equation from these gas laws, right? Right, let's do the stuff. So when it comes to Boyle's law, so it is kind of a PV relationship, right? We know that volume is proportional to pressure, right? So when it comes to Charles' law, we had just derived that volume is proportional to absolute temperature, right? When it comes to Avogadro's law, we derived that volume is proportional to number of moles, right? 1 is 2 is 3. All the relations are actually right connected to the volume. So if you are to consider 1, 2 and 3, we can write the volume, sorry, this is 1 over P, no? Sorry for that, right? 1 over P. Also, no? So we can write the volume is proportional to N proportional, right? Proportional to NT over P. So we can get rid of this proportional sign by using a constant, right? So E is equal to, we can use a constant. So that constant is written as R. R is the proportionality constant, right? Ultimately, we call it as the universal gas constant anyway. It is, that is the constant used to get rid of the proportionality, right? So if you are to rearrange this one, you will get the PV is equal to nRT. Right now, this is how we are supposed to derive the ideal gas law with use of three ancient gas laws. All are related to volume, right? Boyle's law, right? Volume is proportional to 1 over P. Charles' law, volume is proportional to T. Avogadro's law, volume is proportional to N. So volume is proportional to NT over P. We can get rid of this proportional sign by a constant that is written as R, which is the universal gas constant. So P is equal to nRT. Right now, so that is the derivation of ideal gas law with use of three gas laws. Right. So let's come up with the next derivation as well, which is appearing in your note, right? The combined gas law. The combined gas law, right? Let's derive that stuff as well. The combined gas law. So actually, combined gas law is derived for a constant amount of gas. For a constant amount of gas, right? For a fixed amount of gas, right? Fourth gas law, combined gas law. This is derived for a fixed amount of gas. So we can write for a fixed amount of gas, it's like this now. For a fixed amount of gas, right? PV is equal to nRT. No? Fixed amount of gas means N is a constant, right? R is always a constant, so you can write it as PV over T is equal to nR for a constant amount of gas. This is a constant. So PV over T, the ratio is going to be a constant. So we can write it as K, the constant. So for fixed amount of gas, PV over T is a constant. That is referred to as the combined gas law. Three variables appear in there, right? So application means like this. Let's consider two situations. Let's consider two gas systems where the pressure is P1, volume is V1 and temperature is T1, system 1, and the system 2. P1, V1 and T2, P2, sorry, system 2. The values are P2, V2 and T2. Then for system 1, we can write P1, they both are with the same constant amount of gas molecules, right? The same in. Both systems are with the same in, same number of gas molecules, right? So we can write P1, V1 over T1 as both are with the same number of moles, right? It's a constant. You can write it as K, no? So for the second system also, P2, V2 over T2, it's a constant according to this, right? So as both are equal to K, we can write P1, V1 over T1 is equal to P2, V2 over T2. In this form as well, you can represent the combined gas law, right? Because both are equal to K, no? P1, V1 over T1 is equal to K. Instead of K, you can write the P2, V2, T2, right? Because that is also equal to K, right? So this is referred to as the combined gas law, right? It says for a fixed amount of gas, PV over T ratio is going to be a constant, right? Okay. So that is also there and written. Derivation is also done, right? Right. These are the gas laws. These are the simple stuff there with this topic, right? Gas laws. But the major focus today is actually not about this, all about, right, reading the graphical forms involving with these two variable graphs, right? Let's discuss about those things, right? Graphical forms, right? Right, graphical forms. Representation. Graphical representations, right? Okay. Let's discuss about the graphical representations involved in these two variable situations, right? First, we'll discuss about the PV relationships one can say Boyle's relationships, right? Okay, so we could expect two types of PV relationships, right? Okay, the first kind is the curve between the P and 1 over V, right? T versus 1 over V graphs, right? First consider the situation, pressure versus 1 over volume graphs. So this kind of graph, now we are going to discuss about at your practice. Y-axis is the pressure, at your x-axis it is the 1 over V, right? Okay, so we are not trying to memorize these graphs, right? It is very hard to memorize this, all the stuff, right? So you should be able to come up with the correct shape and compare two curves written at the same graph, right? Those are two learning outcomes of this section, right? You should be able to come up with the correct shape of the curve or line, and then you should be able to compare two lines or curves written in the same graph, right? Those two should be done, right? So you can't memorize the stuff because any axis may appear. This axis may appear with any of these P, V, N and T's as well as the reciprocals, right? Okay, so let's first let's try to come up with the shape of the line or the curve. For that, for the to come up with the shape or the shape of line or the curve, or to come up with the comparison between two curves, right? First you need to come up with the correct equation of the graph. You need to construct the correct equation of the graph. Only by using the correct equation of the graph you can comment on the shapes, as well as you can compare two graphs written in the same diagram, right? So for this thing, actually only the knowledge of two types of curves, two types of graphs would be enough. What are the two types of graphs available in this stuff is actually the y equals mx graphs, y equals mx graphs, this kind, y equals mx, or y equals mx plus c is also known, right? Y equals mx plus c is, yeah, you have a intercept, no? It's y equals mx graph. Or another graph type is the straight line thing, y equals mx plus c, no? Yeah, some intercept is also appearing. Y equals mx is a graph going to the origin, right? The third type of graph you should know is y is equal to 1 over x type of graph, right? That is kind of this. It's a curve. Y is proportional to 1 over x. Sorry, y is proportional to 1 over x. Y is proportional to 1 over x. It's a curve. These are straight lines. True origin. This is a straight line. With the intercept. Knowledge of these three types of graphs would be enough, right? Right? So these are three types of graphs we are going to discuss here, right? Okay, let's try to first come up with the equation. Only according to the equation we can select which kind of graph is this, right? Okay, first how to come up with the equation. So basically when building the equation, what we are trying is, first we are trying to subject the y-axis. always the equations are like y is equal to or y is proportional to. So with the use of Peaker's linearity, we first try to subject the y-axis. After that, we are trying to isolate the x-axis at the right hand side. Right? That is what we are doing. Right? First, we will write the Peaker's linearity and we'll first subject the y-axis. After that, we are trying to isolate the x-axis at the right hand side. Right? That is what we are doing. See? So we can write this thing as PV is equal to nRT. First thing is what? Isolating the y-axis. So P is equal to nRT over V. Isolating the y-axis. Isolating the y-axis. Then from the right hand side we have to isolate the x-axis. First subject in the y-axis, then we have to isolate the x-axis at the right hand side. So what is x-axis? 1 over V. 1 over V. So we can isolate that thing like this, 1 over V. Isolate. Separately you have to write that thing, 1 over V. Right? 1 over V. So these are two axes, right? So you have pressure here, this is the y-axis, this 1 over V is the x-axis. Right? So this one is kind of a, right, is y, this thing is a constant, it's a constant, right? So when considering PV graphs, the other two variables should get constant, right? It's a constant. So we can take it as the m, the constant, and this is your x-axis, right? So this is a y equals mx type of graph. So it's a straight line. It's a straight line. Straight line through the origin. Straight line through the origin. That is the shape of the graph. Straight line through the origin. Shape of the graph. Right now? So it's going to be a straight line like this. Straight line through the origin. Right now? Okay. That is clear, right? So shape of the graph is clear. Right? So this is some background knowledge you should know, right? The shapes of graphs. Right? Okay. So first thing is clear. Shape of the graph is clear. Right? So next thing, next learning outcome should be you should be able to compare two graphs written in the same diagram. You should be able to compare two graphs written in the same diagram. Let's see what that means. So let's say you are with two systems. You are with two systems, right? So you are with kind of two systems. Say both are with O2 gas. This is also O2 gas. Right? Both are at the with the same number of moles, let's say 5 moles. Right? One is maintaining at 100 Celsius, or let's say 300 Kelvin, let's come with Kelvin, 300 Kelvin. The other one is maintaining at, let's say, 500 Kelvin. Right? Temperature, the constant temperature maintained is different with two systems. So what you are doing is you just change the volume of the system and measure the pressure. You just change the volume of the system, keeping the system at 300 Kelvin, a constant, right? Keeping your number of moles and the temperature constant, you are changing the volume of the system and measuring the pressure. And let's say you have drawn a graph like this, right? By changing the volume, measure the pressure, changing the volume, measure the pressure, change the volume, measure the pressure. You came up with one graph there like that. Then the same thing is applied for this thing as well. Just consider keeping the number of moles at 5 moles and 500 Kelvin temperature. You had changed the volume and measured the pressure, right? So then let's say you had came up with another graph like this, right? And let's say you had drawn both the graphs at the same diagram, right? So I don't know, one graph representing, right, 300 Celsius, the other graph representing 500 Kelvin, right? So let's say both are Kelvin, right? 300 Kelvin and 500 Kelvin. One representing 300 Kelvin, other representing 500 Kelvin, right? So our task is to compare these two lines, which represents the 500, which represents the 300, right? Both are with O2 gas, kept with 5 moles. Right, now we are supposed to label correctly which belongs to 500, which belongs to 300. Right? Let's discuss how to label correctly the stuff, right? But normally when we drawing these curves, just write these corners as dotted lines, right? It's very hard to, practically hard to come through here, right? Okay. So let's try to label this up. For this thing, basically you can use the gradient. You can use the gradient. See how we are supposed to use the equation of the curve to compare the lines. So in this case, as this one is a y equals mx graph, your gradient or the slope, right, you see the value of nRT, gives you the value of nRT. Your gradient of slope gives you the value of nRT, right? So when the temperature is high, slope is high. Keeping the same amount of moles, 5 moles, right? R is also always a constant. The temperature is high, slope is high, right? So that is the idea, right? So that is how we are supposed to compare these two, right? You can write when slope is high, the temperature is high, or the temperature is high, slope is high. With the situation with higher temperature, slope is high. So that the slope is high with this one, blue color one, compared to green color one. So blue color one represents the higher temperature, so 500 Kelvin. Green color one represents the lower temperature. That is how we are supposed to compare. Clear? No? So you can do the same thing by keeping the temperature constant and varying the number of moles like this, right? If you do such kind of experiment, when the number of moles are high, the slope is going to be high. Such kind of question also can be asked, right? Clear? No? Right. So this is about the P versus 1O V graphs, right? Just complete the stuff here. Right. Let's come up with the P versus V graphs, right? The second type of curves, P versus V graphs, right? Number 2, P versus V graphs, right? So first thing to do is actually deriving the equation, right? Deriving the equation. So now we are supposed to come up with P versus V graph for the O2 system with 5 moles, right? P versus V graph. So first thing to do is actually first thing to do just to come up with the shape of the curve as well as for the comparison. First thing we need to come up with the equation of the graph, right? So let's come up with the equation of the graph. For that we can start with the P equals nRT. Then we are supposed to subject the y-axis first. So P is equal to nRT over V. Then we need to isolate the x-axis at the right hand side. So you have to isolate this thing. So this is going to be nRT 1 over V, right? So this is your y-axis. This is your x-axis. X-axis is just the V, right? X-axis is just the V. P is your y-axis. X-axis is just the V, right? X is just the V. So this is looks like this is a constant. To consider about variation of two things, other things should kept constant, right? So this is y, right? You can take it as k, a constant, and this is just 1 over x, 1 over x, 1 over x-axis. X-axis is just the v. It is y equals k, k 1 over x. So we can get rid of this k. We can get rid of this k by coming up with a proportional sign. Proportional sign. So this is a y is proportional to 1 over x. Y is proportional to 1 over x. That is kind of a curve. It's a curve. This is going to be a curve. It's going to be a curve, right? The shape is a curve. So first thing to do is just to come up with the shape, right? It's a curve. So it's going to be something like this. Curve. Clear? Let's consider, right? We had done two sets of experiments. With one set of experiments, we had changed the volume and measured the pressure of this kind of system, maintaining the number of moles at 5 moles and temperature at 300 Kelvin. You had changed the volume and measured the pressure and drawn a curve. Then with another series of experiments, right, keeping the number of moles at 5 moles and keeping the temperature at 500 Kelvin, you had changed the volume and measured the pressure and just came up with the second another curve, right? Let's say the two curves are like this. I don't know which one belongs to which, right? Anyway, let's consider two practically observed curves are like this. Two curves, right? Okay, two curves, right? So now we need to compare the two stuff. Compare the two stuff. Which curve belongs to which? Which belongs to the 300 Kelvin situation, which belongs to 500 Kelvin situation, right? So to compare this stuff, we need to use the equation of the curve, right? Okay. So comparing y equals mx is easy. because from the gradient, from the slope, we can gather some information. But there is no gradient here. There is no gradient here for this kind of curves. No gradient here. So how to comment? How to compare the two curves? So this can be done like this, Lamai. So the point here is just consider a constant x-axis to compare the stuff. Just consider a constant x-axis, right? Constant x-axis. So that means the x-axis is v. So I am considering a constant x-axis. Right? Consider constant x-axis, right? So we can write when considering a constant volume, right? Constant v. Okay, idea constant x-axis. Then we can write this thing as, right? This is a constant. This is a constant. So that p is proportional to nRT. As this one is a constant, as this one is a constant. So this is this becomes constant. So p is proportional to nRT. P is equal to nRT k constant. To get rid of that, we can write it as p is proportional to nRT, right? So that when considering this, p will be proportional to nRT. This says when temperature is high, this says when temperature is high, your pressure is high, and when number of moles are high, your pressure is high. This is what it says, right? When temperature is high, pressure is high, considering constant x-axis. When number of moles are high, pressure is high. So now we can compare by considering constant x-axis, right? These are the two respective pressures of the constant volume, right? These are the two respective pressures, and this is the higher pressure and this is the lower pressure. This axis is higher pressure, lower pressure. So this says the higher pressure should appear with the higher temperature. Higher pressure should appear with the higher temperature. So the one with the higher pressure belongs to the higher temperature. So this curve, the green color curve, belongs to 500 Kelvin. The one with the lower pressure belongs to lower temperature. This belongs to 300 Kelvin. That is how we are supposed to compare curves by considering constant x-axis. If your curve is, if your graph is a curve, not a y equals mx, you are not having a slope there, right? No. So just complete this stuff. right now. Okay, let's discuss about the other types of relationships, right? So we just discussed about the PV relationship. Now let's concern about the other types, right? First come up with the VT relationship. VT relationship, right? Okay. VT relationship, right? Right. Okay. I erase this term, right? Now you are familiar with the curves now, curves and the graphs now. Right. So now we are going towards VT relationship, right? Volume temperature ratio. Regarding as Charles relationships. No need to worry about this name, right? Charles or the Avogadro or the boys. No need to worry about that thing. Right? Let's consider the VT relationships, right? So V here, the T here. So now my temperature can be given in Kelvin as well as Celsius, right? Here we'll write with Kelvin, right? So I'll do it small, right? Right? Some space is needed, right? Temperature in Kelvin. Or temperature can be represented in Celsius or theta. Those two types of curves could appear right in your papers, right? Let's concern. First, let's try to come up with the equation of the graph, right? For this one, VT. Right? So we have to start with the P equals in RT. Right? P is equal to in RT. Right? So we have to subject the V first, right? So V is equal to in RT over P. Then we have to isolate the x-axis. This is T, right? Okay. So this is isolating, right? So T. This is the x-axis, this is the y-axis. So we are keeping the N and P a constant, right? So this kind of a constant. So this looks like y equals mx, no? It's kind of y equals mx, right? A straight line, a straight line, straight line. True origin. Straight line, true origin. If the temperature is applied in Kelvin, it's a straight line, true origin, right? Everything is applied in Kelvin, right? Straight line, true origin, right? So you'd observe things like this, straight line, true origin. So I'll draw two lines to compare as well, right? Let's concern both are written for O2 gas with 5 moles. Right? One is representing greater pressure and one is representing smaller pressure. Let's say one representing 1 atm pressure and the other one representing 5 atm pressure. So we need to label these two stuff like earlier, right? So coming to the origin, right? So we can write the corners like this, right? It's hard to achieve the Kelvin zero, right? Okay, so we have to label the stuff, right? We'll label after writing this curve shape as well. First we have to write the things for this thing as well. After that we can label, right? So it is very easy, right? So we can come up with the gradient, the slope. The slope will represent the n and p, right? So we'll discuss that thing, right? So let's discuss the thing appearing with the Celsius thing as well. Celsius thing as well, right? Okay. So we can write, because Celsius thing V is equal to nR P is of this T, right? We can write 273 plus theta, right? 25 Celsius means 298 Kelvin. This is how we are converting, right? Celsius to Kelvin. This theta means the Celsius value. So 25 Celsius means 298 Kelvin. So you have to add 273 to convert to the Kelvin. So Kelvin is equal to 273 plus theta. Kelvin is equal to 273 plus Celsius temperature. Theta is the Celsius temperature. T can represent the Kelvin temperature. So we can simplify this thing as V is equal to, so we have to subject the, so we have to isolate the right x-axis now. So it is going to be n r p is there, that theta comes, theta is your x-axis, is your y-axis, plus this section again, this thing into this is this, right? So this thing is this, right? So 273 in R over P. So this is just like you have a y here, right? This is a constant m, and this is your x, plus this is another constant. It can be taken as the intercept. This is y equals mx plus c, right? So it's a straight line with an intercept. Straight line with an intercept, right? Right. So that's the shape. So you would observe this kind of stuff, straight line with an intercept. So this kind of stuff, straight line with intercept. See? Okay. Straight line with intercept, right? So if you have to compare two things, let's compare. Right. Actually, these lines will overlap at this point, right? That is the minus 223 0 Kelvin situation, right? 0 Kelvin situation from that origin things happens, right? This 0 Kelvin 2 cm means 0 Kelvin, right? This is a system. Okay, this is how the two curves appear. So now let's compare the red ones and the blue ones and the green ones. These are straight lines, right? Should be straight. Right, not straight. Let's try to compare this two stuff. How to compare? So basically, the gradient or the slope will give you the N and P. So greater the slope, greater will be the N, lower will be the P, right? So higher pressure will be coming up with smaller slope, right? So if you need the idea, I'll write it here, as I am lack of space here, right? This is this thing, right? So the final stuff is like slope is actually in ROP. That is the idea, right? When N is high, slope is high. When P is high, slope is low. When the P is high, slope is low, right? So we can use this thing. So greater pressure coming up with smaller slope. So out of these two, the smaller slope is this one, that belongs to the greater pressure. So 5 atm belongs to that. Smaller pressure coming up with greater slope. Right now, 1 atm here. 5 atm. Right now, things are clear. Right. So just complete the stuff here. Right. Let's discuss about the last type of curves, which is related to Avogadro's, the V-N relationships, right? This is about the V-N relationships as well, right? V in V right? Okay. Let's try to draw these two curves. Right. First, draw the V in relationship like this. V versus in. Right. V versus in graph. V versus in graph. Let's draw that thing. So how to come up with this thing? Again, first try to subject the y-axis. So P is equal to NRD. So y-axis is B. Just subject that thing. P is equal to NRT over P. Then from the right hand side, isolate the x-axis. The same. Isolate the x-axis. So just isolating this one. So you can write the in from here. Isolate the x-axis, right? This is your equation. So you clearly see this is a constant. So it's a y equals mx, no? It's y equals this m, this x. So it's a straight line to origin. Right? So the shape of the curve should be like this, straight line to origin, right? Right. So let's try to compare two curves. Right? Let's try to compare two curves. Right. Try to compare two curves at same pressure by varying the temperatures anyway. Right? Autographs at 180. So we are varying the temperatures 300 to 500. So which belows which, right? Okay, let's compare. So that comparison can be done with the use of the gradient here. So your gradient, the slope, so y equals mx, no, this is easy, right? So P is equal to RT over P. So this says when T is high, slope is high. T is high, slope is high. When pressure is high, slope is low. Pressure is high, slope is low. Right? So you can use that thing. So this says higher temperature comes up with the greater slope. So greater slope is this one. So that guy belongs to the higher temperature. So that is higher temperature. Sorry, it is 500 Kelvin. The less slope means it is with the lower temperature. Right, no? So this is the V N relationship, right? So just complete this stuff now. Let's complete one. Right. Let's draw the last curve for today. So it is going to be V versus 1 over N graph. Let's draw that thing as well. Right, V versus 1 over N graph. Right, V versus 1 over N. right? So 1 over n here. At the x-axis is the 1 over n appearing, right? So V versus 1 over n graph. First, let's subject the y-axis. PV is equal to nRT. V is equal to nRT over P. Then we need to isolate the x-axis. So this can be written as V is equal to RT over P and N. But this is not your x-axis. This is not your x-axis, right? Yes, y-axis is okay, but this is not your x-axis. Your x-axis is 1 over n. So you can write this n is equal to 1 over n. That is true, no? This is right, no? N is equal to 1 over n. So it becomes to the top, no? So we can write like this thing as n is equal to, right, 1 over n, right? Okay. Right now. So now we can copy the stuff, right? So this is a constant. This is y-axis. V is the y-axis, right? Is equal to constant into 1 over is 1 over x, ne? Is 1 over x. 1 over n means x. So this can be written as y is proportional to x. Y is proportional to x. So it's a curve. This is a curve. This is a curve. Right? So sorry. 1 over x. This is a curve. Right? So it's a curve like this, right? This kind of a curve. So we'll compare two stuff now. Curve is okay. Now we'll compare two stuff, right? With two different temperatures. Right? How to compare curves? You don't have slopes here with the equation to compare curves. So we need to come up with a constant. We need to come up with a constant x-axis. So 1 over n constant. To come up with a constant x-axis. Right? So we can write, when considering a constant, right, 1 over n, that means constant x-axis. When this thing is a constant, we can say V is proportional to RT over P. When this thing is constant, V is proportional to RT over P. So we can write, then V is proportional to RT over P. Right? When this one is a constant, when considering the constant x-axis, this is a constant. So we can say V is equal to RT over P into a constant. So getting rid of constant means V is proportional to RT over P. So this says when temperature is high, V is high. The temperature is high, V is high. Temperature is high, V is high. Temperature is high, V is high. When the pressure is high, V is low. The pressure is high, V is low. So we are considering the same pressure, right? So the one with the greater V representing the greater temperature. See how to compute that. So match these things. So this is the one with the greater V. Vx is no greater V. This is the one with the lower V. Right? So green curve is the one with the greater V. So that represents the greater temperature. Right? So the temperature is what? We are considering two temperatures. Let's say right, 300 and 500. So this represents the 500 Kelvin. The one with the lower V represents the lower temperature. Right now, that is how we expect to copy the curves, compare the curves, right? Okay, so complete the stuff. Right, no? Okay, Lamai. So that is all for today's lesson, right? We had just completed the gas lesson, right? So this is all about graphical representations, right? So the major stuff, the most important stuff we have learned today is the graphical representations. Just follow these things because these will appear in your MCQs. Definitely these things will appear in your MCQs. For the second term test, most probably at the structured question, as a structured question also, these graphical forms will appear right now. So just study these ones. No, don't try to memorize these ones. Just logically first derive the equation of the curve and use that curve to copy the shapes as well as the comparison of two graphs written in the same diagram, right? Okay, so that is the idea. So we'll wind up at this stage. So then goodbye, see you next week.